All right, Harmony Science Academy AP Calculus students, let's go ahead and get into today's section 4.1, Antiderivative and Indefinite Integration. Okay, we've come a long way. You guys have done awesome. Keep putting in that time, and it's definitely going to continue to pay out. Okay, as far as vocabulary, we do have the PDF version of this section, so you guys can go ahead and take time, complete your virtual notebook. And here, let's begin some note taking, okay? Now, the formalities are definitely in the PDF textbook. Here, let's go ahead and just break it down to practical terms, okay? So, antiderivative, literally acting against derivative, okay, or the opposite of derivative, okay? So, just like you have addition and subtraction, multiplication and division, we now have the antiderivative, or it didn't fit here more formally, okay, indefinite integration. Okay, we'll talk about definite integration later. Okay, so again, let's just let's just get to work, right? Let's complete this worksheet. So as you guys read through this section, this here, right, this f of x, and by the way, this symbol here, it's a symbol for integration, okay, or for antiderivatives. So that we can read this one way, okay, I'm gonna do two, as the integral of 5x to the fourth power. This is basically the function f of x, okay, more formally the integrand, and this would be the variable of integration, right, d of x. So just like with derivatives, right, when we differentiate, we need to know in terms of what variable. That's what this serves, okay? Now, as I approach these and you guys approach these, this is going to end up being very simple, which you guys deserve. Okay, you've put in a lot of time. But I want you to really think about the process, since it is the reverse of derivatives. The way we proceed here, okay, and the first 10 are a reflection of the power rule, okay? So you're going to be utilizing the power rule of integration, and it's pretty much the opposite of the power rule in differentiation, okay? So let's go ahead and put that into action. So when it came to derivatives, what you guys would do is what? You would take the old exponent, right? You'd multiply by the old exponent, and then you'd subtract 1 to create a new exponent, okay? Here, the opposite would be what? Literally the exact opposite would be first, right? Reverse the order, add 1 to the exponent, okay? And not multiply, but divide by the new, okay, exponent. All right, so let's go and try that out. So we're gonna have, in this case, okay, what the book would recommend, again, preparing you for more sophisticated problems, is for you to separate that constant, very similar to what we did with differentiation. And here we're gonna go ahead now, okay, and we're gonna go ahead and add 1, and now divide by that new exponent. Okay, notice that I'm literally doing everything about as opposite as possible. Okay, so I've integrated, okay, x to the fourth in terms of x as such, right? Adding 1 to the exponent, then dividing, okay, and this is no longer necessary because we've integrated in terms of x. But what we're going to have here is what is called the constant of integration, okay? Now, let me, for example, write this right here, okay? And by the way, this in reduced form would be what? We've got multiply and divide by 5, so we've got x to the fifth plus c, okay? So the big question at this point is, what's up with this c? So let's take a look at that here real quick. That's it. So, and what I'm doing here is what I'm going to recommend you guys do, what the textbook recommends you guys do, is always check, especially in the beginning, your integration by doing the opposite, right? Taking the derivative, differentiating your results, see if you can get back. So This represents, again, a constant, right? So let's look at any constant. Okay, so let's look at two scenarios. X to the fifth. Let's put the 2 constant. X to the fifth, negative 2, another one. Okay. If I was to differentiate, what do you guys know to do? Right, we would go ahead and I'm doing it very informally here, okay? But you guys have known to bring down, to multiply by this current exponent, right, the old exponent, and subtract 1. You try and do that to that, that reduces to 0, so we're left with this, okay? And if we were to apply it to this one, once again, we'd multiply by the old exponent, subtract 1, and we'd produce a new 4. This would reduce to 0. As you guys can see, there's a whole family, okay, of possible candidates. Okay, so we describe all these constants, okay, all these versions with a plus c. Okay, now later on in certain contexts, as we move forward, we're gonna find a particular solution. So we'll care about a function that crosses through a specific x and y. We'll look at those examples, and we'll even get into some problems that involve motion. Okay, but for right now, this is our introduction, so hopefully that is sufficient for you guys. Okay, so the first what is it, 6 are very straightforward. The next 4 are a bit more challenging. Okay, one tip I'm going to give you guys that the textbook also gives you is these situations where you have a quotient. Okay, do not proceed by taking the integral, okay, of the top separate and the integral of the bottom, right, the denominator. Don't do that. Remember, it's a lot more complex than that. If you look at the rule for differentiation, right, the quotient rule, there's more to it than just applying it straightforward. Okay, don't get the whole L'Hopital rule involved here. Okay, L'Hopital rule is its own criteria. Okay, so just putting it out there. So in this case, one tip, I'm not going to solve these two, but what you want to do is translate x to the fifth down here as a denominator and put this as a numerator. Okay, so then you'd be able to let's go ahead and do a little something here. Okay, so when you guys get here, you'll be a little more comfortable. So here what we can do is break it apart in this way. Okay, plus okay, and one step further, and you guys should be okay. Let's do the third. This would be essentially times x to the negative fifth plus 16x to the negative fifth. Okay, and integrate that way. Of course, you can combine such and such. Okay, all right. So that's going to help you guys survive 1 through 10, and then we get to 11 through 20, which is still more of this antiderivative indefinite integration process, except now you're going to involve trigonometry. Okay, as intimidating as that might sound, you guys have a formula chart, so that's exactly what you'll be using. All right, so for the sake of this video, so it's not too long, let's go ahead and try 12. Okay, again, it's not as intensive as is implied in trigonometry. Okay, you have a formula chart, apply it, and you're done. Okay, so here in this case, let's go ahead and separate out that constant. Okay, we've got cosine x dx. What you guys can do is actually look at the formula chart and see what is cosine x integrated. Okay, so if you're going to integrate cosine x in terms of x and you said sine, excellent. So we got negative 4 sine x. And of course, since we're integrating, we know already that this constant of integration can represent all constants, right? So this represents a general solution. Okay, it's basically a family of them, and not until other contexts will we actually get a particular solution. Okay, so once again, here's the integrand, Here's the variable of integration. Here's the constant of integration. All right, we'll go and catch you in the classroom.